Okay, so thank you very much. As if it's a pleasure to be here today to talk about this topic. Thank you for proposing this topic. It's something I have worked a lot on during my PhD. In fact, I will not talk only about spin diffusion, but in general, the consequences of high electron polarization in our conditions. Before I jump into this topic, I will give a short introduction on dNP and polarization. So, as many of you know, in NMR, we fight with low polarization. So first, what is polarization? If you have a spin half in a magnetic field, there are two stationary states, alpha and beta, when it's aligned or antiparallel with the field. And polarization is the excess of one of these states over the other one, P. And why do we want high polarization? It's because the signals that we record are proportional to the polarization. And when we don't apply hyperpolarization, the polarization is really weak. Here you see the Boltzmann equilibrium, which gives you the value of this polarization. And in the case of proton and carbon spins at a field of 7 Tesla, the polarization is below 10 to the minus 4, 10 to the minus 5 at room temperature. But Albert Overhauser had a great idea in '53, which was confirmed the same year by Carver and Sichter, to borrow the polarization from the electron spins. Why the electron spins? Because they have a larger gyromagnetic ratio and hence a larger polarization. And Overhauser's idea was to transfer this polarization using micro irradiation. And in the conditions that we use in dissolution dNP, we place ourselves in the conditions where the polarization is really near unity. To have ideal polarization after dNP. And the dissolution process, dissolution dNP is a multi-step process where we start in the solid state at below 2 Kelvin usually at moderate field. To reach 2 Kelvin or lower, we need a pumped liquid helium cryostat. And I said we need electron spin. So in our case, we use stable organic radicals as a sort of electrons, and we use microirradiation to transfer the polarization to the nuclei. Once the sample is hyperpolarized, we dissolve it with a burst of superheated water and transfer it to a MRI scanner or NMR spectrometer for use in the liquid state. So that's the workflow of a dissolution dNP experiment. And today I'll be talking only about what happens in the solid state at low temperature and moderate field. I will not be talking about dNP mechanisms in themselves, and for this I suggest there are great lectures in this lecture series, one by Monu Kaushik and a recent one by Professor Ramanathan. Both are excellent, so I suggest you have a look at them if you are interested in dNP mechanisms. Now we'll be talking mainly about relaxation at low temperature, and this is closely related to what Christian Banks and Malcolm Levitt has published a few years ago. So the fact that relaxation cannot be explained well using grid field theory when highly polarized. So to treat them properly, you need so-called Lindelad theory. Luckily, in our case, we'll be in a situation where we can circumvent this complex theory using a simple model. And now I'd like to introduce you to my favorite formula. Those who have read my PhD dissertation have seen this formula a hell of a lot because it's present throughout my work. And this tells you about the nuclear relaxation rates when it is dominated by electron flip-flops. So when you have an electron undergoing flip-flop and the nucleus experiences this, you have a relaxation rate which depends on the polarization of the electron PE. And R0 being the rate that you would observe if the polarization was near zero. And then we can also add a residual source. Sometimes this is the relaxation is dominated, but you still have some relaxation by other processes. If you take conditions of magic angle spinning dNP, even at very high field at 800 megahertz, the polarization of the electron is about 10%. So this 1 minus p square term is very near 1. That's why people usually don't care about it. But in dDNP conditions, the polarization of the electron is really high, very near 1. So 1 minus p squared is in turn very small. So you have to take care about this. But when you switch on the microwave irradiation, you decrease the electron polarization. And hence, you increase this 1 minus p squared by a very significant amount. So you will switch on relaxation processes. And this is what we will play with today. As a first very simple example, we can have a look at T1 relaxation. And here I have measured proton and carbon relaxation as a function of temperature in 2 archetypical samples. And this is at 7 Tesla. Moving temperature means that I'm moving the electron polarization. And so I can translate this measurement into R1 as a function of 1 minus p squared. And I find a reasonable correlation in both cases. So the formula that I have shown earlier seems to apply to this. So now for the rest of this talk, I would like to show first using a simple relaxation model where this paramagnetic relaxation rate comes from. Then we'll see in the literature where this has been observed, effect on the T2 of electrons, T2 of nuclei, and the T1 row of nuclei. And then we will see how we can apply this for different applications. And I will stop a few times to give you the occasion to ask questions. First time will be after this theory part. So I'll be using the easiest model possible for relaxation, which is the random fluctuating field. So we will see the electron as a classical field acting on the nuclei and causing relaxation. To have T1 relaxation, you need transition between the alpha and the beta state, and this is caused by a random fluctuating field, as I said, in the simple model. And this field needs to be fluctuating at the Larmor frequency omega 0. In numbers, this is how you calculate it. So you have your perturbation, which has a certain strength, and this perturbation needs to be along x or y, so it needs to be perpendicular with the magnetic field. And then you have this j omega, which is the spectral density, which tells you the probability of finding this fluctuation at the Larmor frequency of the nuclei. Then you may also express this in terms of fields experienced by the nucleus along x and y. For T2, we have a slightly similar situation where we have this omega x and y term, but we also have a dependence on the fields along the z-axis can also contribute, but with a different correlation function. Oh, sorry. Oh. Trying to use the pointer. Yeah, but the spectral density here is at 0. So for the field along Z, it's not a spectral density at Larmor frequency, but at 0. And again, you can express it in terms of fields and not nutation frequency if you want. But now we know what we are searching for. We need to find the strength of this interaction and calculate the spectral density. So in our case, the interactions between the electron and the nucleus is what we call the hyperfine interaction. We'll be only dealing with the dipolar part, so the through-space interaction and not the Fermi contact. And this interaction has 2 parts, what we call the secular part and the pseudo-secular. The secular part is for the nucleus is a field along the z-axis, and for the pseudo-secular, it's along the x and y axis. And they have different angular dependence that I'm representing here. And you have the constant here, which tells you and which gives you these functions. But because we are using this random fluctuating field model, we will not treat the electron as a quantum mechanical object. And so in the nuclear space, we can replace the Z operators by simply the expectation value. We don't deal with it as a quantum mechanical object. Now, with this, we can calculate the nutation frequencies of the amplitude of the perturbation. From this, assuming that I have to get these numbers, I have placed the nucleus and the electron along the x-axis, and then I have only a field along the x-axis and not along the y. So this tells you that For the T1, which is sensitive to these two numbers, it will be sensitive to the pseudo-secular interaction, while T2, which is sensitive to all three of these strands, it will be sensitive to both the secular and pseudo-secular terms. Now we have the strands of interaction. We still need to calculate the spectral density. And for this, we will need to calculate the autocorrelation function. With time, the electron oscillates between the plus 1 and -1 polarization. And of course, we cannot deal with a stochastic function like this, so we'll replace it by an autocorrelation function. And to construct this autocorrelation function, we'll assume that if we know the polarization of the electron at time 0, the electron is going with time, with a characteristic time tau c, to an equilibrium value. And so if we start from +1, we go to this equilibrium value, and again from -1. And more formally, we can define the autocorrelation function in this way as a sum of the different processes. MS could be higher than plus or minus a half if we are dealing with high spin radicals, but here I will be only talking about spin half. And we have the autocorrelation function for each of these processes, which is the product of the polarization at time 0 and a long time. So in our case, for spin half, we have two functions for the electron starting at +1 and -1 polarization, and here the polarization at time 0 and the polarization over time. It is a little complex, but I really wanted to explain it because once you sum the two processes with their different weights here, you get this 1 minus p square term. So this term pops up when you construct the autocorrelation function. And we did not need any other arguments to get to this term than assuming this autocorrelation function. Now, with our autocorrelation function, we're first going to make a little shift. We remove this term here because it's not decaying and it's not causing relaxation. And when we take the Fourier transform of it, this is where we obtain our spectral density function, which tells us the probability to find the electron oscillating at a frequency omega. So this is what we were after, and we see that this spectral density, which is a Lorentzian, bears the 1 minus p square term. And you can represent it this way. So this tells you that for example, a correlation time of 1 microsecond, you have this dispersion of probability of finding the electron at different frequencies. This is everything we need to calculate our R1. And this we have calculated on the previous slides. It becomes this, and the spectral density comes from here. If you plug in the expression for the pseudo-secular term, this is what you get. And I would like to say that there's a good chance that I have a factor 2 missing somewhere. What I'm showing here is more the reasoning, and I apologize if there are mistakes, but the idea is here. And when you look in the literature, often you will see this rate expressed without these constants here, because people often average over all orientation to get rid of this variable. And also often you don't see this term because people assume low polarization, so this goes to 1. And in our conditions, very often the correlation time can be considered large in front of the Larmor period, and so this 1 here becomes small in front of this number, and our rate simplifies a little bit. It becomes inversely proportional to the correlation time. There's one thing I have hidden under the carpet for now, which is where this correlation times come from, and I'm going to give a very short explanation for this. But usually we consider that the electron can decorrelate because of two processes, spin-spin interaction and spin-lattice interaction. In our case, electrons interact strongly, and the decorrelation is dominated by the dipolar interactions between the electrons. So the decorrelation rate is on the order of the dipolar interaction between the electrons, and this is the full expression for this. For dNP juice with 50 millimolar of radical, the distance between neighbors is on the order of 2 nanometers, and this leads you to approximately 1 megahertz of decorrelation rate, and hence a correlation time on the order of the microsecond. Now we have seen the expression for T1. We can do the same with T2 by plugging the terms, and this, as I said, was due to the pseudo hyperfine interaction, and this one to the hyperfine interaction. But again, if we consider that we have a correlation time that is large in front compared to the Larmor period, J omega 0 would be large in front compared to the spectral density at frequency 0 would be large in front of the spectral density at the Larmor frequency. And hence, only this term contributes to T2, and we have these two quite simple expressions for T1 and T2. Now I'm going to show where these dependencies have been observed in the literature, and maybe this is time to answer a few questions if people already have it on this theory part. Oh.
As of now, there are no questions, Quentin.
Okay.
So you can proceed.
Okay, good. So I carry on. So we will see some examples where people have observed this dependence. I start with a paper by Mark Sherwin and co-workers, and this is in NV centers in diamonds. So we are not talking about nuclei, we're talking about electrons, but the process is the same. Electrons cause the other electrons to decorrelate. And they explain it in a different way that what I have shown now. They say that the R2 is proportional to this product of population. And why is that? Is because when electrons are in dipolar interaction, they will only undergo flip-flops if they are antiparallel. And the probability to have them antiparallel is given by this product. And then you can express it in terms of these Zeeman factors with the ratio of the Zeeman temperature and the lattice temperature. This is very different to what I've explained so far. But in fact, when you do the math, this is exactly equal to this 1 minus p squared. And experimentally, how does it? What does it look like? So they have measured the T2 at very low temperature, 1.3 Kelvin. You see this slow decay, and at room temperature, this very fast decay. And here it's the rates as a function of temperature, fitted with this model, which explains the relaxation all the way from 1 Kelvin to 300 Kelvin, which is quite remarkable. Then again, Mark Sherwin with other collaborating with Sanghehan and others, where they have used the same model to explain T2 relaxation of electrons in a matrix with tempo in a disordered frozen solution. And just here, they don't call it T2, they call it the phase memory time, which is in the wording of EPR. And I just picked one out of the many results of this paper. I've picked one result that I find interesting, where they show that this rate here is proportional to the third power of the distance between electrons. And they say in the paper that this is expected from the literature. I just wanted to check with my simple model if I could explain this. And in fact, so the R2 it can be calculated as the R2 for the nuclei. But instead of the hyperfine interaction, we have the dipolar interaction between the electrons here. And we have seen that the decorrelation rate is on the order of the dipolar interaction between electrons. And hence, the expression simplifies to this, and the dipolar interaction is in itself proportional to the third power of the distance between electrons. And so we find with our simple model what they have found experimentally. So it's a sort of confirmation of this simple model. Now I move to a paper by Geoffrey Bodenhausen and co-worker in Paris, where they have observed that gating the microwaves had an effect on the T2 of the nuclei. This is, I said dNP juice, this is dNP juice and other materials, but in all cases, frozen solutions. And this is an interesting result where they are recording a dNP buildup, as we often do, but in this case, using a solid echo. In the beginning, they see the polarization increasing as expected. And when they switch off the microwave radiation, you would expect naturally that the signal goes down. But in fact, in this case, it goes first up and then down. And why is that? It's because when you switch off microwave radiation, you let the electron relax, and hence this 1 minus p square term becomes much smaller, and so the losses during the echo are also smaller in turn. And again, as Mark Sherwin, Sanghi-Han, and others, they explain the relaxation rate in terms of this product of probabilities to find the electron in the alpha and beta states. And they show that it is equal. This is equal to the model I have shown so far. So now I move to applications. How can we take advantage of this? What can we do with this? And now I turn to a paper by my supervisor, Sami Jana, and again, Shafiq Bolanazans and others, where they look at the effect of the polarization of the electron on the T1 row of proton spins. They use a slightly, this is the model I have shown. In the paper, they use a slightly different model, but I don't want to go into the details. Just for simplicity, I will explain what happens using this model. So the pulse sequence that they use, you first polarize the proton spins, shining microwaves. Then you switch off the microwaves. You wait a time that is sufficient for the electrons to relax. And then this is a spin lock sequence where you put the protons in the transverse plane, spin lock them, and then bring them back along the z-axis and read out what remains along the z-axis. And these are decay curves as a function of the spin lock time. So this tells you how the nuclear spins relax in the transverse plane during the spin lock. And if you don't gate the microwave, you see these different curves at several temperatures between 1 and 4 Kelvin. And if you gate the microwave, then you have much less relaxation due to this 1 minus p squared term. The polarization of the electron is higher if you gate the microwave, and hence the relaxation is lower. And once you have measured at different temperatures the R1 row, you can get these A and B terms, and hence you will be able to measuring the T1 row in conditions where you don't know the electron polarization. You will be able to calculate the polarization from your T1 row. Again, this is not exactly the model that they use, but this is for simplicity. So now we are able to know the polarization also when the microwave is on. And in that case, they measured and then calculated that the polarization on the microwave irradiation was about 50% at 1 Kelvin and almost 7 Tesla. Then they went further, and this is where it becomes very interesting, by playing with this gating delay here. If you make it very short, at the moment where you do your spin lock, the electrons have not relaxed yet. And it means that you are still measuring the R1 in conditions where the electron is still weakly polarized. And the more you wait, the more the electron is polarized, and the less you will see relaxation. So this is what you see as a function of the gating delay. So you keep the spin lock time constant this time, but you increase the gating delay. You see this increase in signal. And then on the final panel, using the model I showed earlier or something similar, you are able to extract the polarization of the electron from this curve, the bottom curve, and hence they could measure a T1 of the electron on the order of 50 milliseconds at 1 Kelvin. Even further, another application that is really interesting for dissolution dNP is when you do a cross polarization from the proton, the carbons, you can take advantage of this. So you polarize in the first step the protons using dNP. You gate the microwave to let the electron relax, and then you do your CP. And what you see is that if you have gated the microwave, you have this blue curve here as a function of the spin lock time, or the CP time here. But while if you don't gate the microwave all along, you don't go as high in polarization simply because you have too much losses during the CP. And in a multi-CP experiment that you see here, all these discontinuities here, this is a long time after a few minutes, you let the proton polarize, you do a CP to transfer from the proton to the carbon, and again, so each discontinuity corresponds to a CP. And when you gate the microwave before doing a CP, you have a much better result than when you don't gate them. So this is a very nice application of the microwave gating to increase your efficiency of CP.
Can I ask a quick question, Quentin?
Yeah.
In your previous slide, so is this T gate time same as the T1 of electron, the buildup?
T gate here?
Yes, the
So
buildup.
this is a parameter you increase.
Similar to T1 of electron?
It needs to be, yeah. So you will, it needs to be on the order of the T1 of the electron. So you gate from 0 to 5 times the T1.
It's almost 100 millisecond at this condition.
Yeah, so they found 50 milliseconds. Yeah.
Okay, thank you.
You're welcome. So now I think that's, oh yeah. So now I'm moving to result that I have acquired. I wanted to see if we could do the same with the T2 of the carbons. So I use not Temple in dNP juice, and I looked at the natural abundance carbon spins in dNP juice, and this is the pulse sequence I use. I first polarize the protons, gate the microwave to have an efficient CP, transfer the polarization from the proton to the carbons, and then I record the T2 of the carbons with a solid echo. I did this at several temperatures, so each of these curves corresponds to R2 measurements at a different temperature, and hence at a different electron polarization. And then I can plot these rates against 1 minus p square and extract the A and B terms. So these parameters now I will be able to infer the polarization of the electrons in conditions where I don't know it, measuring the R2. And you see the fit is rather good. And then I did the same, but with switching on the microwave again during the echo to be able to measure the polarization on the microwave radiation. As I said, inferring the polarization of the electron from the measured R2. These are the, again, measurements, but this time as a function of microwave power during the spin lock. Unfortunately, I'm not able to use different powers here and here. So it means that when I measure with a very low power, I'm also measuring with a very poor dNP. So I have a less good signal. But anyway, I could still measure this R2, and from the R2 extract the polarization, the polarization of the electron. And this is a plot of the polarization of the electron as a function of the microwave power. And in gray is just another model, but that's the details. Then, as Aurélien Bornet and Sami Jeanne and Jeffrey Bodenhausen, I did the same. I played with the gating delay. I did two experiments. One is to measure the T1 of the electron, and the other one is to measure the time it takes for the electrons to be saturated. So to measure the T1, I apply some microwaves during a while, and then I switch off and vary this T1 parameter here. And if I want to measure the time it takes for the electron to saturate, I switch on the microwave and I vary this parameter here. And this is what I got using the same procedure as before as a function of these two parameters, T1 here and Tsat here. I have this polarization that decays in the case of the Tsats and increases as a function of T1. So, and for negative, and I repeated it for negative and positive dNP. The T1 is on the same order of magnitude in both cases, and it's quite close to what was found in the previous paper I mentioned. And the time to saturate the electron is shorter and on the same order of magnitude for negative and positive dNP. And finally, I also use this R1 row of protons to make some measurements. Same process. I polarize protons, gate the microwave, do a spin lock measurement, and I mean, put the protons in the transverse span, do a spin lock, increment it to measure the R1. And these are different curves of the decay of polarization under the spin lock as a function of temperature here. So you see that the lower I go in temperature and hence the higher in electron polarization, the less I lose signal during the spin lock. Then I use these rates to compare them with 1 minus b square. As you can see in this case, my model is maybe too simplistic because there's the residues are not randomly dispersed, but still I consider that it was good enough to try some more measurements and extract my A and B terms here. And hence, from here, I'm able to infer, I try to infer the polarization of the electron from R1 row measurements. And now the idea was to measure an indirect EPR spectrum. So I no longer gauge the microwave here. And what I do is I repeat this measurement for different microwave frequency. And for each microwave frequency, I measure R1 row that you see here, which I can convert into an electron polarization as a function of the microwave frequency. And I do a hypothesis that is similar to what people do in longitudinally detected EPR, LODE EPR, which is to say that the change in electronic polarization when I switch on the microwave is proportional to the number of spins at this frequency. And this means that the number of spins at the frequency is proportional to the change in microwave in electron polarization. And so from this plot, I can get an EPR spectrum. This is the blue one. And I compare it with an easy spin simulation of the temporal spectrum. You can see that the fit is not perfect. I mean, it's not a fit. It's but the comparison is not perfect. So this method gives you a rough EPR spectrum, but of course it's not yet perfect. So I will stop now. The last part will be on spin diffusion. So I will switch topic, and I can take a few questions if there are some.
There is one question by Jeffrey, but that's regarding the theory part. So he's asking, can you comment on the anisotropy dependence of nuclear relaxation rate driven by the dipolar coupling part of the hyperfine?
I would say that, yeah. So there's an angular dependence. Some nuclei will have a stronger in hyperfine interaction, and so relax faster. And also they are at a distribution of distances to the electron. I think the answer is different if you are talking about T2 or T1, because for T1 you will have spin diffusion that will make the problem even more complex. For T2, spin diffusion is not really play a role, but of course you can expect that because some nuclei are far further away from the electron, they will have a weaker relaxation rate. What I found surprising is that for the carbon spins, I found that they were well fitted by a monoexponential, which I did not expect. I thought it would be a stretch precisely because of this reason, but experimentally that's not what I observed. Maybe it's simply because you have so many electrons that you also need to take into account not the closest electrons, but the others that I'm not really sure.
Okay.
There's another question.
Let me check. Yeah, there is another by Fred Mentic. He's asking, do you think the fact that there is spectral diffusion under microwave irradiation, does that explain why the moderate agreement between experiment and simulation of the tempo line? So whatever you have on the slide right now.
Yeah, that's a good question, and I must say I'm not really sure. It could be part of it. Yeah. So spectral diffusion. First, I would say that maybe we have too much. Sorry.
He's talking about electron spectral diffusion.
Yeah. First, maybe we have too much microwave power, so we are saturating the spins. we are saturating too much, and so this proportionality is not conserved. And then spectral diffusion can also play a role. The thing is, if you are not oversaturating, it should not change too much for this 1 minus p square. I think I cannot give a clear definite answer, so I should not try. But I think that you are probably on the right path.
I have a simpler question here. So why doesn't your polarization on the top rightmost plot go to 0 when you're doing microwave saturation?
I think it's simply because we don't have enough microwave power. That's one thing. And also
the T1 is quite long. T1 of T1 is almost 50 millisecond. So you should be able to saturate even with.
Yeah. Then maybe this is another point where the theory is quite simplistic. When you switch on microwave radiation, we don't burn a hole in the EPR line in our conditions. What happens is so we have this some negatively polarized electron and positively polarized electron. This is the thermal mixing theory, and so I think this is again a reason why the model is simplistic. So maybe the polarization is even lower, the average one, and this explains why we measure something higher.
One thing that you can do to eliminate the effect of spectral diffusion is further dilute your electrons, maybe 5 millimolar.
Yeah, that will be more difficult, but that would be interesting.
Okay, so there are no further questions. So
it'd be interesting to have it would be much better to do these experiments in a setup where you can compare either by LOD, ESR, or the experimental setup. Now it's not even published. I'm showing you results that are. I don't know how we would publish this because we don't have the control experiments together with it.
So there are no questions at this point of time. I think we can proceed with the talk.
Okay. But I saw that someone raised their hand, I think.
We'll take that question later.
Okay, good. So now I move to the last part of this talk, which might sound a little surprising that I'm talking about spin diffusion in this context. But we will see that spin diffusion is also affected by the electron polarization. To start with, let me give a brief summary of why, of the concept of spin diffusion. So spin diffusion was introduced by Boltzmann in the 40s to explain relaxation in insulating solids where the electrons cannot move. And Blomberg's model is a two-step mechanism where electrons flip-flops induce nuclear relaxation near the electron only because of the dependence on distance of the hyperfine interaction. And then in a second step, spin diffusion transmits this effect to the rest of the nuclei. Spin diffusion is the flip-flop, so the transition from alpha beta to beta alpha of the nuclear spins in this case. What Blomberg realized already in 49 is that for the nuclei that are very close to the electron, the alpha beta and beta alpha states are no longer degenerate, and this makes the flip-flop not energy conservative, so it's quenched. And now, even decades after Blomberg has proposed this model and it was improved in many ways, it is still very difficult to know at which point this effect stops being a problem. So what we call it the spin diffusion barrier, this radius where spin diffusion is quenched, and we don't really know, does the electron polarize nuclei that are far away and this transmits the bulk, or spin diffusion is efficient nearer, and then the very strong hyperfine interaction can be used to do dNP and then this diffuses spontaneously. There are no general ways to measure this. So we introduced a method called the hyperpolarization resurgence experiment, which consists of first polarizing. You start with non-polarized nuclei, you polarize them homogeneously with dNP. Then you switch off the microwave and you saturate the spins. And the saturation pulses have a limited bandwidth, so they will only act on the spins that you set them so that you only act on the visible spins, and you have spins that are further away from your NMR line because they are too much hyperfine shifted, and your pulse don't affect those spins. So you create a gradient of polarization between the spins that are very near the electrons that you cannot observe and those further away. Then you record the signal equilibrating between the two until it reaches equilibrium. As an example, this is a curve at 3.8 Kelvin in dNP juice at 7 Tesla, where we have polarized the spins with positive dNP and then saturated the visible spins and recorded a disequilibration. So first, we see the polarization raising because the polarization that was not affected by the pulses near the electron resurges onto the visible spins. And if you start by doing negative dNP before saturating, then you see this negative overshoot. And as you can see, it reaches thermal equilibrium, which is a very small value as compared to this overshoot. So the effect is quite strong. From the slope of this curve, you can infer the rate at which polarization exchanges from hidden to visible spins. And that's what we will use now. And for comparison, this is standard saturation recovery. And we repeated this measurement at different temperatures between 1 and 4 Kelvin. And then I fitted it with a phenomenological model, a very simple one, just to extract the rate. So this is the model, and we get different flow rates as a function of temperature between the hidden and the visible spins. As you can see, the lower we go in temperature, the slower the diffusion from the hidden to the visible spins. And when we measured this, we found it puzzling because we didn't have a good explanation on why spin diffusion would be so dependent on electron polarization. And we were tempted to think, so the question is, what does provide an energy that you need to do this transition to allow spin diffusion? You could be tempted to think that you have motion, vibration is in the sample, and that this will help spin diffusion. There's very little literature on this, but this process exists. But a better explanation is already present in the literature in several papers, and the first one is by Horowitz in 1971, which explains that, again, this is where the electron's polarization pops in. It's that the fluctuation of the electron spin state will compensate for this mismatch here. As you go from 1 Kelvin to 4 Kelvin, this 1 minus p square increases a lot. So this should be a beginning of explanation. To verify this experimentally, we came up with a second experimental scheme where instead of simply gating the microwave here, we switched them back on during detection. And doing this, we repeated for different microwave power during detection. You see these different curves, fit them again with our model. And what we see is that diffusion is faster when you increase the microwave power. When you increase the microwave power, as we have seen, you also decrease the electron polarization. So this is all done at 1.2 Kelvin. And we see from playing with the microwave power, this time not with temperature, but with microwave irradiation. Playing with the electron polarization, this time with the microwave power, we also see that the flow rate depends on the electron polarization. And it's interesting then to compare these two data sets. First, these are the flow rates measured varying temperature to vary the electron polarization. There's just this point here where the model was fitting poorly, so it's sort of an outlier. And then we compare it with the results where we switched back on the microwave irradiation to modulate the electron polarization. And this is, in fact, the reason why I measured the electron polarization using the T2 of the electrons was precisely for this project to be able to compare, and this is what we get. So the blue data points are the one where I have modulated the electron polarization using the microwave power, and I measured this electron polarization using the R2 of the carbon spins. The agreement between the two is reasonable, especially here. Of course, this is an outlier, as I said, and if I go back to the data, you will see that the model fits very poorly here. But I think this is a rather convincing experimental proof that the polarization of the electron is the determinant for the spin diffusion. And we have also worked on a more theoretical explanation for this, which is based on Horvitz model and some improvements, but I won't talk about it today. But this is all I wanted to say for spin diffusion. But in conclusion, to conclude this talk, I see 3 points. First, electron flip-flops dominate nuclear relaxation in our conditions in insulating solids. It should be noted that if you have moving electrons, then it is a completely whole story because you have another mechanism that kicks in. And when the electron polarization goes to unity, this completely fizzles out the spin dynamics. But it's almost as everything was getting silent. Nothing is happening in the sample anymore. And as we have seen, we can exploit this phenomenon for a number of applications, including spin diffusion and efficient CP and indirect EPR measurements. With that, I would like to thank the funding agencies who have made this work possible and many co-workers. First, my supervisor Sami Janin, and all the people from the team. There are 2 master students who worked with me on these different projects, Pierre and Alessandro, and the former members of the team, Samuel, Stuart, Olivier, Morgan, and Theo, and people from our institute and some collaborators, Arthur and Frederic, who contributed to the work on spin diffusion. Some results I have not shown on the magic angle spin and the interpretation of the results. Thank you for your attention. I'm happy to take questions.
Thank you, Quentin. That was a wonderful talk.
Thank you very much.
So to all the audience, please type in your questions in the Q&A. We have one question unanswered so far. So it's again related to slide number 27, I think.
Yeah.
Yes. So there's a question. How do you calculate polarization percentage from your data?
This is again using this formula. So I have I assume that the R1 row has this form. I measured A and B using this correlation, and then in the other experiment, for each data point I measure R1 row, and then I calculate PE using this A and B coefficients.
So these are all relative relative to something. They're not absolute polarization, or is it absolute polarization?
This is absolute. Yeah.
Okay.
Absolute, of course, with probably a lot of systematic error, but it's absolute.
Let me check Q&A. So we are still waiting for questions. While we wait, I have a couple of more questions. So regarding the second part of the last part of your talk, so you saturate and then you wait. You saturate the bulk nuclei and then you wait and you see a polarization transfer, most likely from the core nuclei.
Yeah.
Right. So, and then you showed that with different microwave power, you can change the rate of the transfer. So I have a question. You had your famous rate equation where you showed if the relaxation of the nucleus, if you're doing flip-flop, would relaxation rate would increase. So the moment you turn microwave on, you have some microwave radiation, the core electrons, the core nucleus, they would lose their polarization also, right, to an extent?
Yes, and thank you for asking, because
I see like in your experiment, in your data, for all different microwave power, you reach the same 3% polarization. So if the relaxation of the nucleus is also changing, I think the next slide.
Yeah, this one.
So yeah, it reaches the same polarization for all power, but the relaxations are different for all power. So how do you explain this effect?
Yeah, this is really interesting, and I think this is precisely where the model breaks down. It's that I use the random fluctuating field model, which works sort of fine for T2, but for T1, it's not a random field. You have paths with different energies, and this is in fact to describe it properly, you need to describe the nuclear bath, the Zeeman bath, in contact with the electron dipolar bath. And these energies, it's not that the electron dipolar bath has an infinite energy compared to the Zeeman, which would be a necessary hypothesis to use a random fluctuating field model. So it works to some extent. And here, I think what you have said is the fact that they all go to the same polarization is really the proof that during this time, which is about seconds, you have almost no relaxation. Relaxation is too slow to be effective, so you have almost only diffusion. And the big difference is diffusion needs the help of the electron, but in this case, the energy associated with the transition is much smaller. It's not a net change of magnetization of the sample in diffusion. It's only you see what I mean? It's because it's a flip-flop. It's not as much energy as really flipping only a single nucleus. It doesn't ask as much energy to the electrons.
Okay. So this is still very sophisticated talk for me. I'll have to rewatch to understand all the sciences that you have explained. But regarding this, so when you do this microwave, you are basically doing a transition within the electron level. And you are doing transition with a rate which is proportional to microwave power. And that is a very small power, whereas your hyperfine coupling is very strong. So is there a correlation, like at what microwave power, at what microwave power the spin diffusion or like microwave power is also like, it's also doing, it's averaging the dipolar coupling also. So there is both decoherence and there is both, there is decoherence also, there is decoupling also. So what's the optimal power, like as per your prediction?
I think this is, again, it's that I think we can completely neglect the effect of microwave directly on the electrons. Because remember that our microwave power is small and it saturates a very tiny part of the EPR line. So it decreases the electron polarization for these tiny parts, but it affects the whole line because of spectral diffusion. So I don't think we can really say that because our microwave power is weak, it's not averaging out the hyperfine interaction. And if it does a little bit, it's only for a very small subset of spins. But it does, because T1E is long, it affects the whole EPR lines through spectral diffusion. And most of the effect comes from the fact that you switch on dipolar flip-flops between the electrons when you decrease the electron polarization.
Okay, so there are two more questions on the same, in fact, three questions. So one is like, when you say the electron flip-flops provide the energy to overcome spin diffusion barrier, is it the same electron generating the barrier or some other electrons in the environment?
When you say oh yeah, that's an interesting part, interesting question. Is that in fact you can see the electron as, you can decompose the electron as two parts: a static part, which is proportional to the average electron polarization, and this oscillating part. So yes, it's the very same electron which is able on one side to shift the levels and prevent spin diffusion, but this very same electron is also able to induce spin diffusion.
Okay.
And this idea is really already in the paper by Horvitz.
Okay. And Arthur has a question: how analogous are proton-driven spin diffusion between carbon nuclei and the electron-driven spin diffusion between protons?
I think they are very related, but it's also related to the previous question. In the case of proton-driven spin diffusion, the energy mismatch between the carbon states is usually due to CSA, I guess, and the nuclei, the protons are giving the energy mismatch, well, compensating for the energy mismatch. While in the electron-driven process, it's the electron which does both jobs, as I just said.
Okay. And there's a final question by Jeffrey. Do you ever see evidence of hole burning?
So I guess by asking this, Jeffrey, you mean as opposite to the establishment of a spin temperature in the dipolar line? I don't. I just assume that our hole burning turns into, because of fast spectral diffusion turns into a dipolar temperature in the for the electrons, because of what I know of the literature. But I have never seen experience of neither hole burning nor dipolar temperature.
Okay.